Hello everyone. On this video we will be going over concavity. Okay, so here's I guess you could say the idea that would explain concavity. Okay, so what if we let f of x be differentiable on an open interval? And we'll call that interval I, and that's from x equals a to some x equals b. Okay, so first, if the graph is what we call concave up, then the graph lies above, that's the key word there, all tangent lines in that interval. All tangent lines in the interval from A to B. Alright, so to kind of help you visualize it, let me make sure that's focused as well as it can be. Yeah, that's pretty good. Alright. So, let's say if you have your XY axis. Okay, you have your X and you have your Y. And you have a graph that looks like that. Okay, and this is what we call concave up. Okay, so let's say this is x equals a and your interval x equals b. So from A to B, every part of this graph is above the tangent line. Okay, so let's say if your tangent line is here, and you have a tangent line here, and you have a tangent line here, and you have a tangent line there, and you have a tangent line there. Okay, so you notice all of your tangent lines are on the outside of the graph. So all the tangent lines, well, the graph is on the inside or above your tangent line. Okay, so that's how you know it's concave up. Okay, now second, if the graph is concave down, then the graph lies below all the tangent lines. Below all tangent lines in that interval from A to B. Oops. Alright, make sure that's up a little bit there. Alright, so once again, just to help you visualize it, let's say we have our XY axis. This is your x-axis, and that's your y-axis. And you have a graph that looks like that. Okay, so let's say it's between the interval x equals a to x equals b. Alright, so if we see all of our tangent lines here, we see that our tangent lines are above the graph. Okay, so the graph is below all of our tangent lines. And this is concave down. Okay, so kind of a little hint to help you, distinguish one from the other. Hint here, if you have concave up, you have C up. So concave up just says cup. So this is kind of like a cup. So you know if it's concave up, it has the opening of a cup. So just a little hint to help you kind of separate one from the other if you ever get confused. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page, which will give the actual definition of concavity. Alright, so we have our definition. Of concavity. Okay. So what if we let f of x be differentiable on our interval from a to b? The graph is concave up on that interval from a to b if f prime of x is increasing and concave down if f prime of x is decreasing. On the interval from x equals a to x equals b. Okay. Now you're probably looking at that going, okay, what exactly does that mean if it's constantly increasing? Sometimes it's up, sometimes it's down. So let me show you what I mean by that, just in case it's a little bit confusing. Okay, so remember our concave up spells cup. And our concave down. Okay. Now, if you remember, for concave up, your tangent lines are below the graph. And for concave down, your tangent lines are above the graph. Now, if it's concave up, your derivative, or the slope at that particular point, will be increasing. Okay, so you look here, you have a slope here. Now, notice that slope, if you look at it carefully, the slope is not as steep. It's kind of rising up a little bit. And at some point, that slope is going to equal 0. So you have a negative slope, then at some point that slope equals 0. And then the slope increases. So it goes from negative to 0 to positive. Okay, so even though it's basically a steady increasing. So let's say if you have a slope of negative 3 here. Here you may have a slope of negative 1. Then you have a slope of 0. So it's steady increasing as you're going. Now, if it's concave down, your derivative or your slope is going to decrease. So here, if you notice, the slope is kind of high, or your tangent line is kind of high. Then if you see there, it kind of goes down a little. Then it goes down a little more. 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 So it keeps decreasing. So let's say here you could have a slope of 8. Then this one you're going to have a slope of maybe 6. Then here you're going to have a slope of maybe 2. Then it's going to eventually, well, my drawing wasn't so horrendous. It would look a little bit neater. There we go. Alright, so then 0, then go from there. There we go. Okay, so you can see all of the slopes steady getting smaller and smaller. Okay, so you see all of your slopes here f prime of x is increasing. And you see all of these here, all of those tangent lines, they're getting smaller and smaller, so your f prime of x is decreasing when it's concave down. Uh-oh, sorry about that. Alright. So, if you are still writing, feel free to press pause. But we're going to go ahead and move on to the steps to test for concavity. Oops. Alright. Okay, so in order to test for concavity, you follow the steps I'm about to show you. Okay, now before you do that, you have to make sure that f of x is a function that has a second derivative. So let f of x be a function whose second derivative exists on that interval. Okay. Now first, let's say if you find the second derivative and you see it's greater than 0 or it's positive. Okay, for every value of x between a and b. Okay, so it's positive for every x in the interval from a to b. Then we know the graph is concave up. The graph is concave up. Okay. Now what if we find our second derivative and find out that every value is negative? So if f prime of x is less than 0 or negative for every x in the interval from a to b, then the graph is concave down. Alright, so we have if it's greater than 0 and if it's less than 0, what if it equals 0? If your second derivative of x equals 0, the function is linear and concavity is not defined. Okay. So if you have a straight line, it's not concave up or concave down. A straight line is neither concave up or concave down. Alright, so let me slide that up. because now we're going to look at a graph with both concave up and concave down. Okay, so what if we have a graph similar to this one? So let's say if we have our X and Y axis, we have our X, and we have our Y, and our graph looks somewhat like this. Okay, so you have a concave up and concave down. How do we know exactly where one ends and one begins? Where does it stop at concave down? Where does it start at concave up? Okay, so let's say we have some point that we will call C. So this point is C and some f of C. Okay, now the point that separates the concave up and the concave down is actually called, well, that's on the same graph, is called the point of inflection. Okay, so the point that separates concave up and concave down on the same graph is the point of inflection. All right. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page. Oop. That's what the sheet already wrote on. Let me move that out the way. Alright, so to find our point of inflection, let's say if C, the point C and f of C is a point where the second derivative at C is equal to 0 or does not exist. Then that point C, f of C, is called the point of inflection. Or you may see POI written. Alright, so let's go ahead and do a quick example of that one. Okay, so let's say, for example, we want to determine the point of inflection for the graph of f of x equals negative 3x to the third power minus 5x squared minus 9x minus 2. All right. So to solve this one, we know that since the point of inflection is just second derivative at some point that equals 0. We just have to find our second derivative. Okay, so our first derivative, bring down our 3, so that's negative 9x squared. Minus, bring down the 2, so that's minus 10x. Minus 9, and the 2 becomes 0. Okay, so now we find our second derivative. Okay, we go ahead and bring down the 2, so that's negative 18x. Minus, that becomes 10, and that 9 just disappears. Okay, so we want to find out where our second derivative equals 0. Okay, so in other words, we want to know where negative 18x minus 10 equals 0. Alright. So we go ahead and add 10 to both sides. Negative 18x equals 10. Divide both sides by negative 18. You have x equals negative 10 over 18, or negative 5 over 9. Okay, so this is our C for our point of inflection. Well, this is our C for our point of inflection. If you want to find your f of C, you just plug that into your original. Oh, move that upside. There we go. All right, so that's how you would find your point of inflection. All right, so if you are still writing, feel free to press pause. But we're going to go ahead and do one more example. Okay, so let's say for this example, let's say we want to determine if f of x equals 3x to the third power plus 7x squared plus 9x minus 2 is concave up or concave down at x equals 1. Alright, so to do this, you want to remember that f prime of c, well, f double prime of c is greater than 0, means it's concave up. And your second derivative at c is less than 0, means it's concave down. Excuse me. Okay. Now remember, in this problem, your c is equal to 1. So we just have to find our second derivative, plug in our c, and see if it's positive or negative. Alright, so we find our first derivative, f prime of x is equal to, bring down our 3, so we have 9x squared, bring down our 2, plus 14x, that becomes plus 9, and our minus 2 becomes 0. So to find our second derivative, bring down that 2, that gives us 18x, plus 14, and that 9 becomes 0. Okay, so now at x equals 1, remember your c in this case is equal to 1. Second derivative at 1 is going to equal 18 times 1 plus 14, which is equal to 32. So your second derivative f prime of c, or f prime of 1, is 32. So that tells us all we need to know. That our second derivative is positive at x equals 1. Which lets us know it's concave up at x equals 1. Alright, so that is how you test for concavity. Alright, so hopefully this made sense, and I will see you on the next video.